Picture a world so distant and cold that sunlight takes more than 5 hours to reach its icy surface, a place where the sky is perpetually dark and the ground is frozen solid with nitrogen glaciers. This isn't science fiction, this is Pluto, the tiny world at the edge of our solar system that defies expectations at every turn. Once considered the ninth planet, Pluto's demotion to dwarf planet status in 2006 only deepened its mystery. But here's the thing, Pluto didn't stop being fascinating just because we changed its label. If anything, the more we learn about this enigmatic world, the more questions we uncover. From its strangely shifting surface to its towering ice mountains and possible underground ocean, Pluto is a cosmic puzzle begging to be solved. Why does this tiny, frozen rock hold so many secrets? Maybe it's because Pluto exists in a realm of perpetual twilight, where the rules of planetary science seem to bend, or perhaps it's because, despite being billions of miles away, Pluto feels oddly alive, with geological activity, haze-filled skies, and even weather patterns that shouldn't exist on something so small and cold. Every time we point our telescopes or spacecraft toward Pluto, it throws another curveball our way, challenging everything we thought we knew about the outer solar system. And that's what makes it so thrilling. Today we're diving into 25 of Pluto's most baffling mysteries, of phenomena that have left scientists scratching their heads and rethinking textbooks. Some of these puzzles might hint at forces we don't yet understand, while others could rewrite the story of how our cosmic neighborhood formed. So buckle up, because we're about to embark on a journey to the edge of the known solar system, where every discovery raises new questions and where Pluto, the underdog of the cosmos, refuses to be ignored. One of the most striking features on Pluto is the enormous, heart-shaped region known as Tombaugh Regio, a sprawling, bright expanse that immediately captivated scientists when the New Horizons spacecraft beamed back the first close-up images in 2015. Stretching over 1,000 miles wide, this massive heart isn't just a whimsical landmark, it's a geological enigma that defies easy explanation. The left lobe, called Sputnik Planitia, is an icy plain made mostly of frozen nitrogen, carbon monoxide, and methane, smoother than any surface scientists expected to find in such a distant, frozen world. But what makes this feature truly bizarre is its sheer brightness, gleaming white against Pluto's darker, rust-colored terrain like a beacon in the darkness. So why does Tombaugh Regio shine so intensely? One leading theory suggests that the nitrogen ice here is constantly renewing itself, churned up by slow-moving convection currents beneath the surface. Think of it like a planetary lava lamp. Heat from Pluto's interior might be causing solid nitrogen to rise, cool, and sink in an endless cycle, keeping the ice fresh and reflective instead of being darkened by space radiation over time. But here's the catch, Pluto shouldn't have enough internal heat to power this kind of activity. It's tiny, just 1/6 the mass of our moon, and after billions of years, it should have cooled off completely. Yet somehow, Sputnik Planitia remains astonishingly active, reshaping itself in ways that leave planetary scientists baffled. Another puzzle is the heart's uncanny shape. How did such a perfectly defined feature form in the first place? Some researchers speculate that a massive impact billions of years ago might have carved out the basin, and over time, volatile ices pooled inside it, creating the smooth, bright surface we see today. But others argue that Pluto's strange climate could play a role. Perhaps seasonal shifts in temperature cause nitrogen snow to accumulate in just the right way, sculpting the heart over millennia. Then there's the wildest idea of all, that the entire region is slowly drifting, pulled by an underground slushy ocean shifting Pluto's mass like a hidden current. No matter which explanation proves true, Tombaugh Regio stands as a reminder of how little we truly understand about Pluto. What looks like a simple, charming heart from afar is actually a dynamic, ever-changing landscape, one that challenges our assumptions about how small, icy worlds behave. Every time we study it, Pluto seems to whisper the same tantalizing question: if something this strange can exist out here, what else are we missing in the dark reaches of the solar system? If nitrogen glaciers sound like something out of a surreal alien landscape, that because they are, and Pluto's version makes Earth's icy rivers look sluggish by comparison. Unlike the slow creeping glaciers we're familiar with, Pluto's frozen nitrogen flows in ways that shatter every rule of planetary geology. Imagine ice that moves like soft wax, oozing across valleys and pooling into vast, smooth plains, all at temperatures close to absolute zero. These glaciers don't just inch forward over centuries, they might reshape entire regions in a matter of decades, creating a landscape that's constantly in flux under a sky frozen in perpetual twilight. What makes these glaciers so bizarre? For starters, nitrogen ice behaves nothing like water ice. On Earth, glaciers flow due to the weight of accumulated snow compressing into ice, which then deforms under gravity. But on Pluto, nitrogen ice is so soft at -390 degrees Fahrenheit that it can glide across the surface almost like a liquid, even on gentle slopes. Data from New Horizons revealed sprawling glacial lobes spilling into Sputnik Planitia, some stretching hundreds of miles with intricate, cell-like patterns etched into their surfaces. These patterns suggest convection, a process where warmer ice rises, cools, and sinks in a continuous cycle, churning the glacier from within. It's the same kind of motion you'd see in a simmering pot of soup, but happening inside a slab of frozen nitrogen thicker than a skyscraper. The real head-scratcher is how these glaciers get the energy to move at all. Pluto's surface is colder than the darkest shadows of our moon, with barely any sunlight to drive geological activity. Yet here, nitrogen ice doesn't just sit inert, it migrates, evaporates from one area, and recondenses in another, like some kind of planetary scale weather system. Some scientists think Pluto's faint but complex seasons play a role, with temperature shifts just significant enough to sublimate nitrogen ice into vapor, which then snows back down elsewhere. Others propose that residual heat from radioactive elements deep inside Pluto, or even tidal forces from its largest moon, Charon, could be keeping the ice mobile. Then there's the mystery of the glacier's speed. While Earth's glaciers crawl at speeds measured in inches per year, Pluto's nitrogen rivers might surge forward in sudden bursts, propelled by the bizarre physics of exotic ices. Some models suggest they could advance miles in a single Plutonian summer, a season that lasts over 60 Earth years. This hyperactivity defies all expectations for a world so small and cold, forcing scientists to reconsider how geology operates in the outer solar system. The implications stretch far beyond Pluto. If nitrogen glaciers can rewrite the rules of ice dynamics here, what does that mean for other distant worlds? Could similar processes be at work on Eris, Haumea, or even Triton, Neptune's geyser-spewing moon? Every new discovery from Pluto's glaciers chips away at our assumptions, proving that even in the darkest, coldest corners of space, nature finds ways to surprise us. One thing's certain, these aren't your grandfather's glaciers. They're a window into a stranger, more dynamic universe, one where the familiar laws of physics sometimes take a backseat to the whims of frozen nitrogen and the secrets it carries. Stretching across Pluto's eastern hemisphere like a frozen dragon's spine, the Tartarus Dorsal region hosts one of the most otherworldly landscapes ever discovered, a sprawling field of jagged, blade-like ridges that stab into the sky, some reaching heights rivaling skyscrapers. These aren't ordinary mountains, they're colossal shards of ice, some as tall as 500 feet, aligned in eerie, parallel formations that stretch for hundreds of miles. Dubbed the bladed terrain, this nightmarish labyrinth looks less like a planetary surface and more like a surreal art installation carved by forces we barely comprehend. So how did these icy knives form? One leading theory points to methane, Pluto's trickster element. Unlike the nitrogen glaciers of Sputnik Planitia, these ridges might be made of methane ice, a substance that behaves even more bizarrely in Pluto's cryogenic climate. Scientists suspect that over millions of years, temperature swings could have caused methane in the atmosphere to freeze directly onto the surface, building up in layers. Then, as Pluto's faint sunlight hits the ice, the methane might sublimate, transforming straight from solid to gas, leaving behind jagged crests as the softer material around them vanishes. Imagine a block of dry ice slowly eroding into spikes under a heat lamp, but on a planetary scale and at temperatures cold enough to crack steel. But there's a problem with this idea. Sublimation alone shouldn't create such uniform, razor-sharp ridges. That's led some researchers to propose an even wilder process: atmospheric sculpting. Pluto's thin but dynamic atmosphere could be directing winds to carve these blades over eons, like a cosmic sandblaster, etching patterns into the ice. Others wonder if tectonic forces are at play, with Pluto's crust stretching or fracturing in ways that amplify the sublimation effects. And then there's the most unsettling possibility that we're seeing a combination of all these processes, a chaotic dance of chemistry, weather, and geology that defies any single explanation. What makes Tartarus Dorsa even stranger is its stark contrast to the rest of Pluto. While Sputnik Planish's glaciers flow like molasses, this region is frozen in a violent, almost aggressive stillness. The blades cluster in dense packs, their shadows stretching long and black across the rust-colored ground, creating a texture unlike anything else in the solar system. Even Pluto's closest cousin, Neptune's moon Triton, which also has nitrogen plains and geysers, shows nothing like this. It's as if Pluto decided to carve its own alien signature into the ice, a signature we're only beginning to decipher. Could these structures still be forming today? Some scientists think so. New Horizons detected methane hazes in Pluto's atmosphere, hinting that the same processes shaping the blades might still be active. If true, Tartarus Dorsa isn't just a fossilized relic, it's a living landscape, still evolving under a sun so distant, it appears as little more than a bright star. That realization raises even bigger questions. If methane can build these formations on Pluto, could similar bladed terrains exist on other dwarf planets in the Kuiper belt? Could Eris or Makemake have their own versions of these icy spires, waiting to be discovered? For now, Tartarus Dorsa remains a masterpiece of cosmic mystery, a reminder that even in the darkest corners of our solar system, nature finds ways to surprise us. These aren't just geological oddities, they're clues to a richer, weirder universe, one where the familiar rules of physics sometimes take a backseat to the imagination of the cosmos. And with every new discovery, Pluto whispers the same tantalizing challenge: keep looking, because the strangest wonders are still out there, hidden in the dark. When New Horizons swung its cameras toward Pluto in 2015, it captured something no one expected: a sky so blue it could rival Earth's, a breathtaking layer of atmospheric haze glowing like a celestial halo around the tiny world. But this wasn't just any haze, it revealed a labyrinth of over 20 distinct layers, stretching hundreds of miles high, each one a writhing ribbon of microscopic particles caught in a delicate dance between sunlight and Pluto's wispy atmosphere. For a planet with an air pressure 100,000 times weaker than Earth's, this level of atmospheric complexity shouldn't exist, yet there it was, defying every model scientists had built. What creates these ethereal layers? The answer might lie in a cosmic chemistry experiment playing out in Pluto's skies. Sunlight breaks apart methane and nitrogen molecules high in the atmosphere, triggering a cascade of reactions that form tiny hydrocarbon particles called tholins. These soot-like grains scatter blue light just like Earth's atmosphere does, giving Pluto its unexpected azure glow. But here's where it gets strange: these particles don't just float aimlessly. They organize themselves into precise, stacked layers, almost as if some invisible hand arranged them. Some researchers think gravity waves, ripples in the atmosphere caused by winds flowing over mountains, could be acting like a sieve, sorting the particles into bands. Others theorize that Pluto's uneven surface temperature creates rising and sinking air currents, trapping tholins at specific altitudes like leaves caught in an updraft. Then there's the mystery of the haze persistence. Pluto's atmosphere was expected to freeze and collapse as it moved farther from the Sun, yet these layers remain vibrant, even dynamic. Seasonal changes might be key. Imagine nitrogen ice vaporizing from the surface in Pluto's weak summer, injecting fresh gas into the air to sustain the haze. Or perhaps the particles themselves act as a blanket, absorbing just enough solar heat to keep the atmosphere from fully collapsing. Either way, Pluto's sky isn't just a passive backdrop, it's an active, evolving engine, recycling itself in ways we're only beginning to understand. The implications stretch far beyond Pluto. If a world this small can maintain such a complex atmosphere, what does that mean for other dwarf planets in the Kuiper belt? Could Eris or Makemake have their own hidden hazes, waiting to be discovered? Even more tantalizing, these hydrocarbon particles eventually snow down onto Pluto's surface, painting its terrain with organic compounds. That means the same chemistry that creates Pluto's blue skies might also be seeding its ground with the building blocks of life, or at least, the ingredients for it. In the end, Pluto's atmosphere isn't just a scientific curiosity, it's a masterclass in cosmic resilience. Against all odds, this tiny world has crafted a sky as intricate as any planetary giant's, proving once again that in the outer solar system, the smallest bodies often hold the biggest surprises. And as we piece together how these hazes form and endure, we're not just solving a puzzle, we're rewriting the rules of what's possible in the coldest reaches of space. Rising from Pluto's frozen plains like ghostly islands adrift on an alien sea, the water ice mountains of Sputnik Planitia present one of the dwarf planet's most baffling spectacles. These towering peaks, some reaching over 2 miles high, don't sit on solid bedrock as mountains do on Earth. Instead, they appear to float, anchored in a vast, slowly churning ocean of denser nitrogen ice. It's as if someone dropped a handful of colossal icebergs into a cosmic slushy and watched them bob into position, defying every expectation of how planetary geology should behave. How can mountains float? The secret lies in the bizarre physics of ice at cryogenic temperatures. Water ice, the same stuff that fills your freezer, is less dense than Pluto's nitrogen-rich glaciers, allowing it to act like a buoyant material. Imagine dropping a wooden block into a bucket of syrup. The wood stays afloat because it's lighter than the thick liquid. On Pluto, water ice mountains behave similarly, with their massive bases submerged in the nitrogen slush while their jagged summits breach the surface. But here's the catch: these icebergs aren't small. Some span dozens of miles across, making their buoyancy even more startling. The real mystery isn't just how they float, but why they're arranged in such striking formations. New Horizons revealed clusters of these mountains lining the western edge of Sputnik Planitia like sentinels guarding a frozen fortress. Some scientists think convection currents in the nitrogen ice might be organizing them. Hotter material rising beneath the plain could push the mountains into alignments, like bubbles gathering at the edge of a simmering pot. Others propose that Pluto's subtle gravitational anomalies, possibly linked to an underground ocean, are tugging them into position over millennia. Then there's the question of their origin. Where did these mountains come from in the first place? One theory suggests they're fragments of Pluto's ancient crust, shattered by a colossal impact that created the Sputnik Planitia basin. Another posits that they formed through cryovolcanism, ice volcanoes spewing water instead of lava, that built up these structures layer by layer before they became unmoored and drifted into the nitrogen sea. Either way, their existence hints at a subsurface far more complex than we ever imagined. What makes these floating mountains especially captivating is what they imply about Pluto's hidden depths. Their buoyancy suggests the nitrogen ice beneath them isn't uniform. It may vary in density or even conceal pockets of liquid slush. warmed by residual heat from radioactive decay or gravitational squeezing from Pluto's moon, Charon. Some researchers speculate that these mountains could be the tip of a literal iceberg floating not just on nitrogen ice, but atop a subsurface ocean kept liquid by antifreeze compounds like ammonia. The implications stretch beyond Pluto. If water ice mountains can float on nitrogen glaciers here, could similar features exist on other icy worlds like Neptune's moon Triton or distant Eris? Every discovery on Pluto forces us to rethink the limits of geological activity in the outer solar system. These floating peaks aren't just curiosities, they're clues to an unseen, dynamic underworld, one where familiar rules bend and the line between solid and fluid blurs into something wondrous. So the next time you picture Pluto, don't imagine a static, frozen rock. Think of it as a world of slow-motion tides and drifting mountains, where water ice sails across seas of nitrogen like ships in an endless, cosmic night. It's a reminder that even in the darkest reaches of space, the universe still finds ways to surprise us one floating mystery at a time. Near Pluto's poles, the landscape takes on a haunting, almost artistic quality. Long, dark streaks stretch across the icy plains like brushstrokes from some cosmic painter. These aren't random stains, they're precise parallel lines that cluster near the poles, starkly contrasting with the bright ices surrounding them. Some measure hundreds of miles long yet remain eerily uniform in width, as if etched by an invisible hand. When New Horizons first revealed these features, scientists were stunned. How could such orderly, persistent markings exist on a world with barely any atmosphere to shape them? The leading theory points to tholins, those same complex hydrocarbon molecules that paint Pluto's skies blue, but here, they might be acting like cosmic chalk dust. As Pluto's seasons shift over its 248-year orbit, sunlight hitting the poles could trigger chemical reactions in surface ices, creating dark tholins that accumulate over time. Think of it like sun-bleached furniture left outside for decades, except in reverse. Instead of fading, these areas darken as organic compounds build up. But there's a hitch. Pluto's axial tilt is extreme, almost like Uranus's, causing its poles to experience decades of continuous sunlight, followed by equally long periods of darkness. That means these streaks could be recording centuries of seasonal change, layer by layer, like rings in a tree trunk. Yet tholins alone don't explain the streaks' razor-sharp edges or their wind-swept appearance. That's where Pluto's whisper-thin atmosphere comes into play. Even with air pressure 100,000 times weaker than Earth's, winds might still be strong enough to redistribute tholin particles, sculpting them into streaks. Imagine blowing gently across a dusty table. The faintest breath can move fine grains into distinct patterns. On Pluto, nitrogen or methane vapor rising from warmer areas could create micro-scale breezes, pushing dark grains into linear dunes. Some researchers even suggest electrostatic forces might help, with charged tholin particles levitating just above the surface before settling into aligned formations. What's truly surprising is how localized these features are. They cluster near the poles but avoid certain areas entirely, as if repelled by invisible boundaries. This selective distribution hints at something deeper. Pluto's climate isn't just a passive backdrop, it's an active, dynamic system where temperature differences of just a few degrees could create microenvironments, pockets where chemistry and weather conspire to produce these dark signatures. The streaks might even serve as a record of climate cycles stretching back millions of years, preserving clues about how Pluto's atmosphere has expanded and collapsed over time. And then there's the wild card: could these streaks be migrating? On Mars, similar-looking features called slope streaks appear to shift seasonally, driven by dust avalanches. While Pluto's versions are likely formed differently, the possibility that they change over time even slightly raises tantalizing questions. If future missions caught them in motion, it would prove that Pluto's surface isn't just reacting to the present climate, but actively evolving with it. These dark polar streaks are more than just geological oddities, they're a cryptic language written in tholins and ice, waiting to be decoded. Each line might hold secrets about how tiny, distant worlds preserve their histories against the cold vacuum of space. And as we piece together their story, we're reminded that even in the solar system's loneliest outposts, change is the only constant etched in shadows on the ice, one cryptic streak at a time. Towering over Pluto's southwestern terrain, Right Mons looms like a frozen titan, a massive, craterless dome stretching 100 miles across and rising 2.5 miles high. But this isn't your typical mountain. Its flanks slope gently, its summit dips inward like a collapsed souffle, and its surface is riddled with strange, puckered textures. This bizarre structure has scientists whispering one electrifying possibility: we might be looking at the largest cryovolcano ever discovered in the outer solar system. Unlike Earth's fiery volcanoes, Right Mons wouldn't erupt with molten rock. Instead, it could spew a frigid cocktail of water ice, ammonia, and methane, oozing across the landscape like a slow-motion glacier with a mind of its own. Why is this potential icy volcano so enormous? On Earth, volcanoes like Mauna Loa grow large because of repeated eruptions over millennia, each layer of lava stacking atop the last. But Pluto's surface is far colder and its materials behave differently. Cryovolcanic eruptions here wouldn't produce runny lava, they'd expade slurries of semi-frozen slush, thick enough to pile up into steep, towering formations. Some researchers think Right Mons' size hints at an extraordinarily active past, with eruptions persisting for millions of years. Others propose that Pluto's low gravity, just 1/15 of Earth's, allows erupted material to spread less widely, creating taller, more concentrated peaks. Then there's the wildest idea of all, that Right Mons isn't a single volcano but a sprawling complex, with multiple vents feeding its growth like a frozen version of Hawaii's volcanic hotspots. The real cliffhanger, whether this icy giant is still active today. Most of Pluto's surface shows ancient scars, but Right Mons looks surprisingly fresh. Its lack of impact craters suggests it could be relatively young, perhaps even geologically recent. Some of its textured patches resemble flow features, hinting that slushy eruptions might have occurred as recently as a few hundred million years ago, a blink of an eye in cosmic terms. Even more tantalizing, New Horizons detected traces of ammonia mixed with water ice near the structure. Ammonia acts like antifreeze, lowering the melting point of water and keeping subsurface fluids mobile long after they should have frozen solid. If pockets of this slushy mix still lurk beneath Right Mons, the door remains open for future eruptions, but Pluto's volcanic mysteries don't end there. Just northeast of Right Mons sits another peculiar dome, Pickard Mons, equally large and equally enigmatic. Their proximity raises questions about Pluto's internal heat source. Most small icy worlds should have cooled off billions of years ago, yet these structures suggest pockets of warmth persisting deep underground. Could radioactive elements in Pluto's core still be generating heat, or is the dwarf planet's gravitational tug-of-war with its moon Charon flexing its interior like a cosmic stress ball, creating enough friction to melt ice? Every clue points to a world far more dynamic than we ever imagined, one where frozen volcanoes might still whisper with activity under a sky of perpetual twilight. Right Mons forces us to rethink what volcanism can look like in the outer solar system. If icy slush can build mountains this vast, what other cryovolcanic wonders might lurk on distant worlds like Eris, Sedna, or Triton? Each eruption on Pluto wouldn't just reshape the landscape, it could deliver fresh organic compounds to the surface, stirring the pot for prebiotic chemistry. That makes Right Mons more than a geological oddity. It's a potential factory for the ingredients of life, frozen in time yet teeming with possibility. So the next time you picture volcanoes, don't just imagine fiery peaks under tropical skies. Think of Pluto's silent giants where the eruptions are cold, the lava is ice, and the only thing hotter than the mystery is the scientific debate brewing back on Earth. Whether active or extinct, Right Mon stands as a monument to Pluto's defiant complexity, a frozen world that refuses to be simple. Pluto's surface tells two very different stories, one written in the pockmarked scars of ancient impacts, the other in vast, eerily smooth plains that look like they were resurfaced yesterday. Most of the solar system's small, icy worlds are cosmic punching bags, their faces battered by billions of years of collisions, yet when New Horizons zoomed in on Pluto, it spotted sprawling regions, especially within the heart-shaped Sputnik Planitia, that are almost entirely devoid of craters. This isn't just odd, it's a glaring contradiction. A world this old should be littered with impact scars, like the Moon or Mercury. Instead, parts of Pluto appear polished, as if some unseen hand is constantly wiping the slate clean. So what's erasing the craters? The leading suspect is convection, a slow, churning motion in Pluto's nitrogen ice that acts like a geological eraser. Imagine a pot of thick soup simmering on low heat. As warmer blobs rise and cooler blobs sink, the surface constantly renews itself. On Pluto, solid nitrogen ice behaves similarly, with warmer sections bubbling up from below, smoothing out imperfections over time. But here's the twist: convection requires heat, and Pluto, a tiny world barely bigger than Texas, should have lost its internal warmth eons ago. Yet somehow, Sputnik Planitia's ice remains restless, its surface refreshing itself in cycles that might last mere tens of thousands of years, a blink in geological time. There's another possibility, that Pluto's surface isn't just shifting, it's outright melting in places. When New Horizons mapped the dwarf planet's temperatures, it found subtle variations that could hint at sporadic, ice melt events. Nitrogen ice, despite being hundreds of degrees below zero, can soften under pressure or mixed with antifreeze compounds like methane or carbon monoxide. Even a slight warming could turn parts of the ice sheet into a slushy fluid, allowing craters to sag and collapse like footprints in wet sand. Some researchers speculate that tidal forces from Pluto's moon Charon might flex the dwarf planet's interior, generating just enough heat to keep these thaw and freeze cycles going. Then there's the wild card, atmospheric snowfall. Pluto's thin but active atmosphere might play a role in resurfacing, with nitrogen and methane snow gradually blanketing older terrain. Think of it like a cosmic Zamboni machine. Each seasonal shift could dump fresh ice onto the plains, burying craters under layers of pristine frost. This wouldn't just explain the smoothness, it could also account for the bright, reflective patches that make Sputnik Planitia shine like a beacon against Pluto's darker highlands. But the most tantalizing clue lies in the distribution of these smooth zones. They cluster in low elevation areas, particularly within Sputnik Planitia's basin, as if the crater erasing forces favor specific regions. That's led some scientists to propose a radical idea, that Pluto's icy shell is floating on a hidden subsurface ocean. If liquid water sloshes beneath the surface, it could create weak spots where the crust is thinner, allowing more heat to reach the ice above and fueling localized resurfacing. It's a controversial theory, but if true, it would mean Pluto isn't just a frozen relic, it's a world with a liquid heart, still shaping its own destiny. The lack of cratering forces us to confront a humbling truth: Pluto, despite its distance and diminutive size, is far from geologically dead. Whether through bubbling ice, cryptic melt events, or even a buried ocean, this tiny world is actively erasing its own history and rewriting it in real time. Every smooth plane is a fresh chapter, a reminder that even in the solar system's darkest corners, change is the only constant. And as we unravel how Pluto keeps its surface young, we're left wondering, if this small, cold world can defy expectations so spectacularly, what other surprises are waiting in the Kuiper Belt's endless night? Pluto isn't just frozen and gray, it's painted in ruddy hues, like a cosmic canvas smeared with rusty brushstrokes. These reddish-brown stains, splashed across vast stretches of the dwarf planet's surface, aren't random discolorations. They're tholins, complex organic molecules forged in Pluto's wispy atmosphere through a relentless barrage of solar radiation and cosmic rays. Imagine sunlight breaking apart simple gases like methane and nitrogen, then reassembling the fragments into sticky, tar-like compounds that snow down onto the icy ground below. The result? A world dusted with the same chemical precursors that might have jump-started life on Earth billions of years ago. So how does this alien chemistry lab work? It starts high above Pluto's surface, where ultraviolet light from the distant sun slams into methane molecules, tearing them apart. The broken pieces, carbon and hydrogen atoms, collide with nitrogen and recombine into larger, more complex structures. These newborn tholins are far more intricate than their ingredients, forming chains and rings that resemble the building blocks of proteins and nucleotides. Over time, these particles clump together, growing heavy enough to drift down like cosmic soot, coating Pluto's ice in a thin, reddish film. The process isn't quick. It might take millennia for a single layer to accumulate. But in a world 4.5 billion years old, time isn't in short supply. What makes tholins especially fascinating is their resilience. Despite Pluto's extreme cold and negligible atmosphere, these organic stains persist, clinging to water ice like frost on a winter window. Some regions, like the dark highlands of Cthulhu Macula, are so heavily coated they appear almost burgundy against the brighter nitrogen plains. This isn't just surface decoration, it's evidence of an ongoing chemical conversation between Pluto's atmosphere and its geology. When New Horizons analyzed the light reflecting off these areas, it found spectral fingerprints of complex hydrocarbons, confirming that tholins aren't just present, they're diverse, with variations suggesting different formation conditions across the dwarf planet. But here's the real kicker: tholins might be more than passive stains. On Earth, similar compounds created in labs to simulate conditions on early Earth or Saturn's moon Titan have shown a startling property. When mixed with water and energized, they can produce amino acids, the fundamental ingredients of life. That doesn't mean Pluto is hosting alien microbes, of course. Its surface is far too cold, and any liquid water would be buried deep underground. But it does raise a tantalizing question: if tholins are raining down on Pluto, could the same process have occurred elsewhere in the solar system? Could these ruddy molecules have seeded young Earth or icy moons like Enceladus with prebiotic material, kickstarting the long chain of events that led to life? The implications stretch beyond our cosmic neighborhood. Pluto's tholins are a snapshot of chemistry that might be universal, a process that could be unfolding right now on exoplanets orbiting distant stars. Every reddish stain is a clue, a reminder that the ingredients for life aren't rare or special. They're the inevitable result of simple gases, sunlight, and time. And while Pluto itself may be too harsh for life as we know it, its tholin-coated surface whispers something profound. The universe is a factory for complexity, even in the coldest, darkest corners. So the next time you gaze at Pluto's rusty hues, remember, you're not just looking at a frozen world, you're seeing the shadow of life's raw materials, waiting for the right conditions to awaken. Stretched across Pluto's heart-shaped Sputnik Planitia lies a landscape so fractured, it resembles a giant, frozen honeycomb, a labyrinth of polygonal cells, some spanning 20 miles wide, outlined by jagged ridges taller than skyscrapers. These aren't random cracks, they're the fingerprints of a world in slow motion, where solid nitrogen ice behaves like boiling pudding, churning beneath the surface in a silent, chaotic dance. New Horizons images revealed this terrain in staggering detail, showing patterns so precise they look almost artificial, but the forces shaping them are anything but simple. They're clues to a hidden engine powering Pluto's geological heartbeat. At first glance, the polygons seem reminiscent of mud cracks on a dried-up lakebed, but here, the process is inverted. Instead of contracting, the ice is expanding, heated from below and pushed upward by convection currents. Picture a pot of thick soup simmering on a stove where warmer blobs rise, cool at the surface, then sink back down in an endless cycle. On Pluto, nitrogen ice plays the role of that soup, with one critical difference: it's solid. Yet under the right conditions, even solid ice can flow like taffy. The polygons form where these rising and falling currents meet, their boundaries marked by ridges where cooler, denser ice crumples like a cosmic collision zone. The scale of this phenomenon is staggering. Each cell represents a convection unit, with material taking hundreds of thousands of years to complete a single cycle. But the real mystery is the energy source. Convection requires heat, and Pluto, barely larger than Earth's moon, should have cooled off billions of years ago. Yet Sputnik Planish's ice is anything but stagnant. Some scientists point to residual radioactivity in Pluto's rocky core, slowly leaking warmth into the icy shell above. Others propose a more tantalizing idea, that an underground ocean, laced with ammonia or salts, is acting as a thermal buffer, keeping the base of the nitrogen ice just warm enough to stir. Then there's the wildcard gravitational nudges from Pluto's giant moon, Charon. The two worlds are locked in a gravitational dance, and subtle tidal flexing could generate internal friction, like bending a paperclip back and forth until it heats up. If this tidal heating is at work, it might explain why Sputnik Planish's chaos is so localized. The basin sits almost directly opposite Charon in Pluto's sky, as if the moon's pull has orchestrated the turmoil from afar. What makes these patterns even more perplexing is their freshness. Most of Pluto's surface is ancient, scarred by impacts over eons, but Sputnik Planish's polygons show few craters, suggesting the ice is resurfacing itself in near real time, geologically speaking. Some cells even appear to be merging or splitting, like living things adapting to their environment. This dynamism hints at a delicate balance. Too much heat and the nitrogen would melt into a slushy sea, too little and the convection would grind to a halt. Pluto, it seems, has found a Goldilocks zone where solid ice can still behave like a fluid. The implications stretch far beyond this lonely dwarf planet. If nitrogen convection can reshape Pluto's surface so dramatically, could similar processes be at work on other Kuiper belt objects? Might Eris or Makemake have their own versions of this fractured terrain, hidden beneath layers of methane or nitrogen frost? And if a subsurface ocean is indeed fueling this activity, how many other small, icy worlds harbor secret seas? Sputnik Planish's chaos isn't just a geological curiosity, it's a masterclass in how even the coldest, most distant worlds can defy our expectations, turning solid ice into a canvas for cosmic artistry. One thing's certain, Pluto's fractured heart isn't just beating, it's whispering secrets about the hidden forces that shape the edge of our solar system. Pluto's atmosphere shouldn't exist, at least not the way it does. With the sun a mere pinprick in its sky and surface temperatures hovering near -400 degrees Fahrenheit, this tiny world's gaseous envelope should have frozen solid eons ago, collapsing into an icy shell like frost on a windowpane. Yet when New Horizons swung past in 2015, it revealed an atmosphere 100,000 times thicker than expected, a wispy but defiant shroud of nitrogen, methane, and carbon monoxide clinging to Pluto against all odds. This isn't just a scientific curiosity, it's a cosmic rebellion, a middle finger to every model predicting frozen silence at the solar system's edge. What's keeping Pluto's air from vanishing into space? The answer might lie in a delicate dance between ice and gas, driven by the dwarf planet's extreme seasons. Pluto's orbit is a lopsided ellipse, bringing it closer to the Sun for part of its 248-year journey before swinging it back into the deep freeze. During these rare summers, sunlight, feeble as it is, warms the surface just enough to vaporize patches of nitrogen and methane ice, pumping fresh gas into the atmosphere like a slow-motion geyser. Think of it as a planetary breath, in as ices sublimate, out as gases refreeze when temperatures drop. This cycle creates a buffer, replenishing the atmosphere faster than it can escape into space. But there's a twist. Pluto's axial tilt is extreme 120 degrees, meaning its poles take turns facing the sun for decades at a time. When one hemisphere bakes in continuous sunlight, its ice vaults release torrents of gas, while the other side freezes into silence. New Horizons caught Pluto mid-breath, with its atmosphere near peak density, but over the next century, as the dwarf planet retreats from the sun, much of that gas will snow back down, leaving the sky thinner than a ghost's whisper. The real shocker, Pluto's atmosphere isn't just surviving, it's thriving in ways no one predicted. High-altitude hazes, glowing blue layers, and even winds strong enough to sculpt dunes suggest active chemistry and weather. Some researchers argue that methane acts as a thermostat, absorbing sunlight high in the atmosphere and creating a subtle greenhouse effect that slows the freeze-out process. Others point to Pluto's unexpectedly complex surface, where dark tholin-rich patches absorb more heat, creating localized hotspots that boost sublimation. Then there's the wild card, Charon's gravitational influence. Pluto's largest moon might be tugging on its atmosphere like an invisible leash, creating pressure waves or even funneling gas toward the poles. It's a reminder that Pluto isn't just a solitary ice ball, it's half of a binary system, locked in a gravitational tango that could stir its atmosphere like a spoon in coffee. The implications stretch far beyond Pluto. If a world this small can maintain such a dynamic atmosphere, what does that mean for other Kuiper belt objects? Could Eris or Makemake have hidden gaseous cloaks, flickering in and out of existence with their seasons? And if so, does that redefine what dead worlds look like in the outer solar system? Pluto's defiant sky forces us to confront an exhilarating truth. Even in the coldest reaches of space, change is the only constant, and the rules we thought we knew are just waiting to be rewritten. High above Pluto's jagged mountain ranges, something impossible glimmers in the faint sunlight, frost-capped peaks dusted with methane snow, like something straight out of a winter fairy tale. But here's the catch, this isn't Earth. On a world where temperatures plunge to minus 390 degrees Fahrenheit, snow shouldn't behave the way we know it. Yet New Horizons captured unmistakable evidence of methane snow blanketing Pluto's highest elevations, particularly along the jagged ridges of the Al Idrisi Montes and the rugged highlands near Tombaugh Regio. These aren't just thin coatings, they're persistent, thick accumulations that cling to slopes and summits, defying our understanding of how volatile gases behave in such extreme cold. How does methane, a gas we associate with kitchen stoves and swamp bubbles, turn into snow on a world like Pluto? The answer lies in the dwarf planet's bizarre atmospheric dynamics. Unlike Earth's water-based weather, where moisture rises, cools, and falls as rain or snow, Pluto's version revolves around methane. Sunlight, even at Pluto's distance, provides just enough energy to lift trace amounts of methane gas from warmer lowlands. As these molecules drift upward, they encounter colder air near mountain peaks, where temperatures drop even further. The result, methane doesn't just freeze, it skips the liquid phase entirely, transitioning straight from gas to solid frost in a process called deposition. Imagine exhaling on a frigid day and seeing your breath crystallize midair into tiny ice diamonds, except on a planetary scale, but altitude alone doesn't explain everything. Earth's tallest mountains often pierce through cloud layers, creating snowcaps, but Pluto's atmosphere is absurdly thin, barely 100,000th the pressure of Earth's. For snow to form, the air should be too sparse to carry meaningful moisture, yet Pluto's methane snow isn't just present, it's localized, coating specific peaks while leaving others bare. This selectivity suggests something else is at play. Microclimates. Just like Earth's mountains create their own weather, Pluto's topography might be funneling methane-rich winds into certain zones, where rapid cooling triggers sudden snowfall. Some scientists compare it to the way frost forms unevenly on a car windshield, patches of condensation, appearing where temperature and humidity align just right. The snow's persistence adds another layer of intrigue. On most icy worlds, frost would vanish over time, sublimating back into gas under even the faintest sunlight. But Pluto's methane snowcaps endure, hinting at a delicate equilibrium. One theory suggests the snow acts as its own insulator. Fresh methane frost reflects sunlight, keeping the surface colder and slowing further sublimation. Another idea points to Pluto's slow seasons. A single, snowy period might last decades, allowing accumulations to build into thick, stable deposits. Then there's the wild card wind. Trace breezes, too faint to feel but persistent over centuries, could be redistributing methane snow like a cosmic blower, sculpting it into drifts and cornices. What makes these snowcaps truly revolutionary is their uniqueness. No other known world in our solar system has methane snow settling on mountains, not Titan's dunes, not Neptune's moon Triton. Even Mars' water ice caps behave predictably compared to Pluto's erratic frost. This singular phenomenon forces us to rewrite the rulebook on planetary weather, proving that volatiles can behave in ways we've never imagined under extreme conditions. Beyond the science, there's something poetic about these distant snowcaps. They transform Pluto from a static ice ball into a world with seasons, weather, and even a form of precipitation, a place where familiar processes play out in alien ways. Every frozen peak is a testament to the universe's creativity, a reminder that even in the darkest corners of space, nature finds ways to surprise us. So the next time you picture Pluto, don't just see a barren rock. Imagine those silent, snow-crowned mountains where methane falls like stardust and the universe quietly reinvents what it means to be a world. Among Pluto's countless paradoxes, few are as baffling as the dune's wind-carved ripples stretching across its frozen plains like whispers from an alien desert. On Earth, dunes form under thick, gusty atmospheres where grains of sand are tossed and piled by relentless winds, but Pluto's air is thinner than a sheet of tissue paper, with surface pressure 100,000 times weaker than our planet's. So how could this tiny, frozen world possibly muster the forces needed to sculpt dunes? The answer lies not in what Pluto lacks, but in what it hides, a subtle, surprising interplay between ice, sunlight, and the faintest breath of wind. The dunes were first spotted in New Horizons images of Pluto's western hemisphere, nestled against towering ice mountains and sprawling glaciers. Instead of sand, these ripples are likely made of methane or nitrogen ice grains, tiny, lightweight particles that behave more like microscopic snowflakes than rocky sand. But lifting even these delicate specks should require winds stronger than Pluto's wispy atmosphere can produce. That's where the dwarf planet's tricks come into play. Sunlight, despite being 800 times dimmer than on Earth, may provide just enough energy to vaporize surface ice in localized patches. As gas escapes, it could create microbursts of wind, lifting particles in brief, concentrated surges. Picture dry ice sublimating on a lab table, making nearby flakes skitter. Except on Pluto, this process unfolds across miles of frozen plains, with each burst nudging grains into alignment. Another possibility is electrostatic levitation. On airless worlds like the Moon, sunlight can electrically charge dust particles, causing them to hop like popcorn. Pluto's thin atmosphere might allow a similar effect, where charged ice grains lift off the surface and are then caught by gentle breezes, drifting until they settle into rhythmic patterns. Some researchers even speculate that seasonal changes could play a role. Imagine nitrogen snow evaporating in Pluto's fleeting summer, stirring the surface just enough to send particles tumbling downwind before winter's deep freeze locks them in place. What's most striking is the dune's scale. Some stretch for dozens of miles, their crests spaced evenly like frozen ocean waves. This uniformity hints at something extraordinary. These aren't random features. They're evidence of a persistent, organized process, one that repeats over centuries or millennia. leaving its mark with mathematical precision. Whether sculpted by sublimation-driven winds or electrostatic hops, the dunes prove that even the faintest atmospheric whisper can shape a world, given enough time. But the real marvel is what these structures imply about Pluto's hidden dynamism. Dunes need movement, not just of air but of material. Their existence suggests that Pluto's surface is far from static, with ices constantly shifting between solid and gas, grains migrating inch by inch under a starry sky. And if dunes can form here where the wind is barely a sigh, what other impossible features might lurk on worlds we've yet to explore? Pluto's rippled plains are more than geological quirks. They're a masterclass in how even the faintest forces, given eons, can carve beauty into the coldest corners of the cosmos. Pluto may cling to its wispy atmosphere with cosmic stubbornness, but it's fighting a losing battle every second. Vast plumes of nitrogen gas bleed into space at a rate that would empty Earth's atmosphere in a geological blink. The New Horizons spacecraft caught this escape in action, capturing ultraviolet images of ionized nitrogen streaming away from Pluto like a ghostly comet tail. This isn't just slow leakage, it's a hemorrhage, with the dwarf planet losing hundreds of tons of atmospheric material every hour. For a world already on the knife's edge of habitability, this raises a chilling question. Is Pluto destined to become just another airless rock in the Kuiper belt? The mechanics behind this escape are as fascinating as they are destructive. Unlike Earth, where gravity and a magnetic field shield our atmosphere, Pluto is virtually defenseless. Its gravity is too weak to hold gases tightly, and its lack of a global magnetic field leaves it exposed to the solar wind, a relentless stream of charged particles from the sun that strips away molecules like sand blasting a statue. But here's the twist: the escaping gas doesn't just drift off quietly. New Horizons detected a shockwave in Pluto's ionosphere, where solar particles collide with atmospheric molecules so violently that they're catapulted into space at supersonic speeds. Imagine a cosmic game of pinball, where nitrogen atoms are the balls and the solar wind is the flipper, sending them careening into the void. Yet Pluto's atmosphere isn't just passively eroding, it's fighting back. The same sunlight that heats surface ices and pumps gas into the air also creates a temporary buffer against total collapse. When nitrogen and methane ice sublimate, they replenish the atmosphere faster than it can escape, creating a delicate equilibrium. Some researchers compare it to a bathtub, with both the faucet and drain wide open. The water level stays constant as long as the inflow matches the outflow. But Pluto's faucet is seasonal, tied to its lopsided orbit. As the dwarf planet retreats from the sun over the next century, sublimation will slow and the atmosphere could freeze out entirely, leaving only a skeletal whiff of gases clinging to the surface. This raises an even bigger mystery. Is Pluto's atmospheric loss a death sentence, or just a phase in a longer cycle? Geological evidence suggests the dwarf planet has experienced atmospheric collapse and revival before. Dark ancient terrains like Cthulhu Macula might be fossilized remnants of past atmospheres, places where tholin snowed down during colder eras and were preserved like insects in amber. If true, Pluto's sky could be cyclical, breathing in and out over millennia as its orbit and seasons shift. There's even a wild theory that tidal forces from Charon, flexing Pluto's interior like a stress ball, might intermittently heat the ice and trigger new outgassing events, restarting the atmospheric engine from scratch. The stakes of this puzzle extend far beyond Pluto. If atmospheric escape can be this dramatic on a small, cold world, what does that mean for exoplanets orbiting dim stars? Could some of them teeter on the edge of habitability, their skies flickering in and out of existence like cosmic neon signs? And if Pluto's atmosphere does vanish entirely, only to regenerate later, it would prove that even the quietest corners of the solar system are capable of resurrection. For now, every wisp of gas fleeing Pluto's grasp is a reminder: In the endless tug-of-war between gravity and solar wind, even the most tenuous atmospheres have a story to tell, one written in atoms, escaping one by one into the eternal night. Pluto isn't dancing alone at the edge of the solar system, it's locked in an intimate gravitational embrace with its largest moon, Charon, forming one of the most unusual duos in our cosmic neighborhood. These two worlds aren't just neighbors, they're partners in a silent, slow-motion ballet, circling a shared point in space like figure skaters holding hands. What makes this system so extraordinary isn't just their closeness, it's the way they've reshaped each other over billions of years, leaving fingerprints on geology, atmosphere, and even time itself. At first glance, Charon might seem like just another moon, but the numbers tell a different story. With a diameter roughly half that of Pluto, Charon is so massive that the pair doesn't orbit each other in the traditional sense. Instead, they both revolve around a common center of gravity, a point in empty space between them, like the pivot of a cosmic seesaw. This makes Pluto and Charon a true binary system, more akin to twin stars than a planet and its satellite. Their gravitational tug-of-war has even forced them into tidal locking. Both worlds eternally show the same face to each other, frozen in a perpetual staring contest. If you stood on Pluto's Charon-facing side, the moon would hang motionless in the sky, never rising or setting, while the opposite hemisphere would live in endless solitude, never knowing the sight of its companion. But tidal locking isn't just a celestial quirk, it's a geological powerhouse. The constant gravitational pull between Pluto and Charon flexes their interiors like a stress ball, generating heat that might explain some of Pluto's unexpected activity. Sputnik planishes convecting nitrogen ice, the towering cryovolcanoes, even the possible subsurface ocean, all could be fueled, at least in part, by this relentless tidal kneading. Charon's influence doesn't stop at Pluto's surface, either. The moon's gravity is strong enough to warp Pluto's atmosphere, potentially funneling gases toward the hemisphere locked in its direction. Some scientists speculate that Charon might even steal molecules from Pluto's tenuous sky, creating a faint, temporary exosphere around itself, a ghostly echo of its partner's air. The most tantalizing clue to this exchange lies in Pluto's hazy layers. New Horizons detected a strange, thin band of atmosphere stretching toward Charon, as if the dwarf planet were reaching out to its moon. Could this be evidence of particles hopping between worlds? On Earth, such an idea would be absurd. Our moon is too distant, and our atmosphere too thick. But in Pluto's weak gravity and whisper-thin air, escaping gas might just have a chance to make the journey. If true, it would mean these two worlds aren't just dancing together, they're sharing breaths, trading atoms in the coldest, darkest corner of the solar system. Yet Charon isn't just a passive recipient of Pluto's influence. The moon's own surface tells a story of violent transformation. Vast chasms stretch across its equator, likely formed as tidal forces cracked its crust during the locking process. Its reddish north pole, dubbed Mordor Macula, suggests a capture zone for methane particles escaping Pluto, frozen and chemically altered by sunlight into tholin stains. Even Charon's lack of recent geological activity hints at a deeper truth. While Pluto crackles with unexpected energy, Charon appears frozen in time, its internal heat long since spent. Together they're a study in contrasts, one lively, the other quiet, bound together yet forever separate. What does this binary dance mean for the broader Kuiper belt? If Pluto and Charon can reshape each other so profoundly, could other distant worlds have similar partnerships? The more we study this duo, the clearer it becomes. Even in isolation, celestial bodies are never truly alone. Gravity connects them, molds them, and sometimes, like Pluto and Charon, ties them together in a bond that defies simple categorization. They're not just planet and moon. They're a cosmic pair, whispering secrets across the void, secrets we're only beginning to hear. Stretching like a shadowy sash across Pluto's waste, the dark equatorial belt stands in stark contrast to the dwarf planet's brighter regions, a sprawling swath of terrain so deeply stained it almost looks charred. This isn't just a minor color variation, it's one of Pluto's most prominent features, a belt of mystery wrapped around an already enigmatic world. From afar, it resembles a cosmic bruise, its reddish-brown hues clashing with the gleaming white of Sputnik Planitia and the pale highlands nearby. But what created this dramatic divide? The answer might lie in a battle between sunlight, chemistry, and time itself. One leading theory points to tholins, those complex organic molecules that paint Pluto's surface in rusty shades. But here they're not evenly distributed. The equatorial belt's darkness suggests an extreme concentration of these compounds, as if someone spilled a vat of cosmic tar across Pluto's middle. How did they accumulate so densely in this zone? Sublimation could be the key. Pluto's equator receives more consistent sunlight over its long seasons, allowing volatile ices like nitrogen and methane to vaporize over millennia, leaving behind a residue of non-volatile tholins. Imagine a muddy puddle drying in the sun. The water evaporates, but the dirt remains, growing darker and thicker as the process repeats. On Pluto, this cycle might have played out for billions of years, with each sublimation event leaving another layer of dark organics behind, like layers of paint on an ancient canvas. But there's another, more violent possibility: ancient impacts. The belt's mottled texture, dotted with faint circular patches, hints at a history of collisions. If a barrage of objects struck Pluto's equator long ago, the heat from those impacts could have baked the surface, accelerating the chemical reactions that create tholins. Alternatively, the blows might have exposed darker material buried beneath brighter ice, like scraping away frost to reveal soot underneath. Some researchers even speculate that Pluto's belt could be a fossilized record of a colossal impact, one so massive it unearthed a global layer of primordial grime, with the equatorial region preserving it best due to its unique thermal conditions. The belt's sharp boundaries add another layer of intrigue. Unlike Earth's gradual climate zones, Pluto's dark belt doesn't blend into neighboring regions. It stops abruptly, as if an invisible line separates light from dark. This sudden transition suggests something more than simple sublimation or impacts at work. Could atmospheric currents play a role? Pluto's thin but dynamic air might channel tholin particles toward the equator, creating a concentrated band where winds deposit them like snow in a mountain pass. Or perhaps the belt marks a tectonic boundary, where Pluto's crust fractured long ago, allowing darker subsurface material to well up and stain the surface. What makes this feature especially fascinating is its longevity. Unlike Sputnik Planitia's ever-shifting ice or the drifting dunes, the equatorial belt appears ancient, a relic of Pluto's deepest past. Its darkness has likely persisted for eons, weathering countless orbital cycles and atmospheric collapses. If we could read its layers like tree rings, they might reveal chapters of the dwarf planet's history we can't yet imagine, epochs of intense bombardment, climatic shifts, or even phases when Pluto's atmosphere was thicker and more chemically active. The belt's existence challenges our assumptions about small, cold worlds. It proves that even in the outer solar system, where sunlight is faint and temperatures extreme, persistent forces can etch lasting signatures into a planet's skin. Whether sculpted by slow chemistry, violent collisions, or some interplay of both, Pluto's dark equator is more than a curiosity. It's a testament to the enduring power of time and transformation in the cosmos. And as we study it, we're reminded that some mysteries don't fade with age, they deepen, waiting for the right moment to reveal their secrets. Radiating from Pluto's North Pole like cracks in a frozen windshield, a bizarre formation known as the spider stretches across the landscape, a web of fractures so precise they look almost artificial. These aren't random scratches, they're 6 near-identical cracks, each extending hundreds of miles in perfectly straight lines, converging at a single point as if drawn with a cosmic protractor. When New Horizons first spotted this feature, scientists were stunned. Spider-like fractures exist elsewhere in the solar system. Mars has them, even Earth's moon has them, but none look quite like this. Their symmetry, their length, and their eerie uniformity suggest forces at work that we've never seen anywhere else. So what could carve such geometric precision into a world barely larger than our moon? The leading theory points to tectonic stress, immense pressures cracking Pluto's icy shell like an egg, but unlike Earth's tectonic plates, which shift and grind over millions of years, Pluto's fractures might have formed in a single, catastrophic event. Picture an underground ocean freezing over time. Water expands when it turns to ice, and if Pluto's subsurface sea began solidifying, the swelling ice could have strained the crust beyond its limits, splitting it open along these knife-edge lines. The fracture's radial pattern suggests the stress came from a central point, like a balloon stretched too tight until it pops. Some researchers speculate that the spider's heart might mark the site of an ancient cryovolcanic eruption, where pent-up slush exploded outward, leaving these scars as its legacy. But there's another even wilder possibility, that Pluto's cracks are still forming. The fractures appear remarkably fresh, with sharp edges and little erosion, hinting they could be geologically young. If Pluto's interior is still cooling or worse, freezing in fits and starts, new stress could be accumulating right now, preparing to split the ice all over again. Even more intriguing, faint bluish streaks along some fractures suggest recent venting, as if gases or liquids seeped up from below, painting the ice like ink bleeding through paper. If true, these cracks aren't just relics, they're active pathways breathing Pluto's secrets into the void. Then there's the elephant in the room. Why 6 fractures? Why not 5 or 10, or a chaotic network like Europa's crazed surface? Their mathematical precision hints at something deeper, perhaps the way Pluto's crust fractured along pre-existing weaknesses, like glass following a scored line. Or maybe the spider's legs trace the paths of rising mantle plumes, hot fingers of material punching upward in a perfect radial starburst. Even Pluto's odd axial tilt could play a role, distorting stress patterns over millennia until the ice gave way in this exact, symmetrical fashion. The implications stretch beyond Pluto. If these fractures are indeed tectonic or worse, still active, they could rewrite our understanding of how small, icy worlds evolve. Other Kuiper belt objects like Eris or Makemake might harbor similar features, hidden beneath layers of frost. Even more tantalizing, if Pluto's spider is a sign of subsurface activity, what else lies beneath those cracks? Could they be windows to the very ocean that birthed them, a hidden realm where liquid water lingers in defiance of the cold? For now, the spider remains one of Pluto's most haunting mysteries, a silent, sprawling question etched into the ice. It's a reminder that even in stillness, there's movement, even in cold, there's pressure. And sometimes the universe carves its secrets in lines so clean, so deliberate, that we can't help but stop and stare, wondering what stories they're trying to tell. Pluto isn't just a frozen monolith, it's a chameleon, shifting hues over centuries as sunlight etches its surface with the slow brush strokes of chemistry. Unlike Earth's rapid seasonal changes, Pluto's transformations unfold at a glacial pace, tied to its 248-year orbit around the Sun. This isn't merely aesthetic, these color shifts are a cosmic record of the dwarf planet's climate, written in tholins and ice. When New Horizons captured Pluto in 2015, it revealed a world already mid-transition, its northern hemisphere brightening like frost on a windowpane, while its southern hemisphere darkened like aged parchment. But why? The answer lies in sunlight, feeble yet relentless, and the bizarre dance of molecules it triggers on Pluto's surface. At Pluto's heart, quite literally, is Sputnik Planitia, a gleaming basin of nitrogen ice that acts like a mirror, reflecting sunlight back into the atmosphere. As the dwarf planet inches closer to the Sun during its elliptical orbit, this reflection intensifies, warming the surrounding air just enough to vaporize patches of methane and nitrogen ice. These gases rise, react with solar radiation, and transform into tholins, those reddish-brown organic compounds that stain Pluto's surface like cosmic rust. But here's the twist: this process isn't uniform. Pluto's extreme axial tilt means each pole spends decades in continuous sunlight or darkness, creating stark contrasts. When one hemisphere basks in perpetual twilight, its ices sublimate, feeding the atmosphere with fresh gas that eventually snows down as dark tholins elsewhere. The result, a slow-motion seesaw of color, with one half of Pluto brightening while the other darkens over centuries. The real magic happens in the details. Near the poles where sunlight strikes at shallow angles, methane frost accumulates in thick, bright layers, reflecting up to 80% of incoming light. Meanwhile, equatorial regions like Cthulhu Macula, already rich in tholins, absorb heat, deepening their rusty hues as surrounding ices vanish. This isn't passive staining, it's feedback loop geology. Darker areas absorb more warmth, accelerating sublimation and exposing even more dark material beneath, while brighter zones stay cold, preserving their frosty sheen. Imagine a patchwork quilt where every square competes for dominance, some soaking up sunlight to grow darker, others deflecting it to stay pristine, but sunlight isn't the only artist here. Pluto's atmosphere plays puppeteer, redistributing these pigments with the faintest breath of wind. Thin as it is, the atmosphere can carry tholin particles like dust in a desert breeze, dusting some regions while sparing others. Seasonal pressure changes caused by nitrogen ice vaporizing in summer and refreezing in winter might even create microclimates, where localized winds sweep dark grains into dunes or pile them against mountains. Over millennia, these whispers of weather leave vivid strokes on Pluto's canvas, painting a portrait that's never quite the same from one century to the next. The implications stretch beyond aesthetics. These color shifts could be clues to Pluto's hidden reservoirs of volatile ices. If certain regions darken faster or retain brightness longer, they might mark underground deposits of nitrogen or methane, slowly leaking to the surface. Some scientists compare it to tree rings, each hue variation, a record of climatic shifts, atmospheric collapses, or even cryovolcanic events. And if we could decode this palette, we might predict Pluto's next act. Will its current brightening trend continue, or is another dramatic darkening phase on the horizon? What's truly humbling is realizing we're witnessing just a snapshot of Pluto's epic color cycle. Humans have studied this world for less than a single Plutonian season. Our entire observational history is a blink in its chromatic symphony. Yet even this glimpse reveals a world alive with change, not frozen in time, but evolving, breathing, and rewriting itself under a sun so distant it's barely more than a star. Pluto's shifting hues are a reminder, even in the darkest reaches of space, there's no such thing as stillness, only rhythms too slow for mortal eyes to see in full. And somewhere in the centuries to come, another palette awaits, already brewing beneath the ice. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, should be cosmic wreckage magnets. Their jagged potato-like shapes scream violent pasts, likely sculpted by collisions that sent debris flying in all directions. Yet when New Horizons scanned their orbits in 2015, it found no trace of rings, dust clouds, or even faint sparkles of scattered fragments. This absence isn't just odd, it defies logic. In a system where gravity is weak and escape velocity slower than a speeding bullet, ejected material should linger for eons, like confetti frozen midair. So where did all the broken pieces go? The leading theory blames Charon, Pluto's hulking moon-turned partner. With half the diameter of Pluto itself, Charon's gravity dominates the system like a boulder in a pond, creating chaotic ripples that could swallow debris before it settles into rings. Picture a cosmic vacuum cleaner. Every time a collision chips off fragments from Styx or Kerberos, Charon's gravitational influence might fling them outward into deep space or drag them down onto its own battered surface. Some simulations suggest these moons even orbit in safe zones, where their paths avoid the most unstable regions of Charon's pull, leaving their immediate surroundings eerily clean. But Charon isn't the only suspect. Pluto's wispy atmosphere, though thin, could act like a slow-motion broom. Escaping nitrogen and methane molecules might collide with drifting debris, nudging particles just enough to alter their trajectories over millennia. Think of it like a game of interstellar billiards. Each gentle tap from atmospheric gas sends debris spiraling until it either crashes into a moon or drifts away entirely. And then there's solar radiation. In the absence of strong magnetic fields, charged particles from the sun could electrostatically repel dust grains, pushing them out of the system entirely. The real stumper is the moons themselves. Their surfaces show no fresh scars or craters that would hint at recent smash-ups. If they're not actively generating new debris, could their violent histories be ancient, so old that any traces of past collisions have long since vanished? Or worse, are we witnessing a cosmic magic trick? Some researchers propose that the missing debris isn't missing at all, it's hiding in plain sight as ultra-fine dust, particles so small they're invisible to cameras, but could still coat the moons like a faint, gritty frost. New Horizons instruments weren't designed to detect such subtle material, leaving the door open for a ghostly veil of micron-sized fragments. Whatever the explanation, the silence of these moons speaks volumes. Their pristine orbits force us to rethink how small bodies interact in binary systems, where gravity isn't just a force, it's a sculptor, a thief, and sometimes a ghost. If Pluto's little moons can hide their scars so completely, what other invisible dramas are playing out in the darkness beyond? Infrared scans of Pluto reveal a thermal enigma. Instead of the uniform cold expected from a frozen world, pockets of the surface glow subtly warmer, like embers in cosmic ash. These hot spots aren't random. They cluster in specific regions, particularly around Sputnik Planitia and the fractured terrain near Tartarus Dorsa, where temperatures can spike a few degrees above their surroundings. On a world where surface readings typically hover near -400 degrees Fahrenheit, even this faint excess heat is glaring. What's fueling these anomalies? The answer could rewrite our understanding of what simmers beneath Pluto's icy facade. One possibility lies buried deep underground: residual heat from radioactive decay. Pluto's rocky core, though small, contains traces of uranium, thorium, and potassium elements that release energy as they break down over billions of years. Normally, this warmth would dissipate into space long before reaching the surface, but Pluto's nitrogen ice insulation might trap it like a thermal blanket, allowing hot spots to form where the crust is thinnest. Imagine a pot of soup left on low heat. Even if the flame is tiny, the lid keeps the warmth concentrated in certain spots. Sputnik Planitia's lack of craters and active convection already suggests geological vitality. Could these warm zones be venting that hidden energy like steam through cracks in the ice? Then there's the wildcard composition. Pluto's dark equatorial belt and tholin-stained highlands absorb sunlight more efficiently than brighter ices, creating localized warming. But the infrared data reveals something stranger. Some hotspots don't align with visible features at all. This hints at subsurface variations, like patches of methane clathrates or ammonia-rich ices that conduct heat differently than surrounding nitrogen. On Earth, underground oil reserves alter surface temperatures detectably. On Pluto, exotic ice cocktails might do the same, turning the dwarf planet into a cryptic thermal mosaic. The most tantalizing theory involves friction. Pluto's gravitational tug-of-war with Charon flexes its interior, generating tidal heat that could bubble up through weaknesses in the crust. If Sputnik Planitia sits atop one of these strained zones, like a blister over a wound, it might channel that energy upward, warming the ice from below. Europa and Enceladus owe their subsurface oceans to similar forces. Why not Pluto? New Horizons even spotted possible cryovolcanoes hinting at lingering warmth. If true, these thermal anomalies aren't just curiosities, they're breadcrumbs leading to a potentially habitable underground sea, but the plot thickens when comparing day and night readings. Pluto's rotation is slow. A single day lasts 6 Earth days and 9 hours, giving surfaces ample time to bake or freeze, yet some hotspots retain their warmth surprisingly well during the long Plutonian night, as if something beneath is constantly reheating them. This persistence points to an active heat source, not just sunlight leftovers. Could underground slush oozing toward the surface maintain these zones, like geothermal springs in Earth's Arctic? Or do they mark the birthplaces of next century's nitrogen glaciers, where fresh ice will eventually erupt and spread? What makes these thermal quirks so revolutionary is their defiance of category. They're not purely geological, atmospheric, or compositional. They're a cocktail of all three, blended by Pluto's unique physics. Every warm patch is a puzzle, a flare in the dark suggesting that even in the solar system's coldest reaches, heat finds a way to emerge, sometimes quietly, sometimes in bursts, but always with a story to tell. And if we learn to read them, these anomalies might reveal Pluto's most guarded secret, that even small, distant worlds can cling to their warmth against all odds, whispering of fire in the ice. Scattered across Sputnik Planet's vast nitrogen glaciers, a labyrinth of polygonal pits stretches as far as the eye can see, each one a geometric wound in the ice, some spanning miles wide with edges so precise they look laser-cut. These aren't random divots, they're a network of cosmic sinkholes, their formation a puzzle that has divided planetary scientists since New Horizons first revealed their staggering symmetry. Are they scars from volatile gases escaping into the void, the fingerprints of subterranean heat bubbling upward, or something far stranger, a process we've yet to imagine unfolding in the slow-motion geology of Pluto's frozen heart? The leading theory pins the pits on sublimation, the direct transformation of ice into gas under sunlight's faint kiss. On Earth, sublimation carves penitence, those eerie, spike-like snow formations found in high-altitude deserts. But Pluto's version operates on a grander scale. As sunlight warms the nitrogen ice, patches might vaporize unevenly, leaving behind depressions that grow wider and deeper over millennia. The polygon's angular shapes could emerge from stress fractures in the ice, like mud cracking as it dries, guiding the pit's expansion along pre-existing weaknesses. Picture a sheet of brittle toffee shattering into geometric shards, then slowly dissolving at the edges, except here, the process unfolds across centuries, with each pit a testament to the patient erasure of ice by sunlight. But sublimation alone doesn't explain everything. Some pits cluster in tight, honeycomb-like arrays, their walls steep and fresh, as if excavated by a hidden force. That's where convection enters the debate. Sputnik Planet's glaciers are famously restless, churned by heat from below as warmer ice rises and cooler ice sinks. Could these pits be collapse features, where rising blobs of slushy nitrogen burst through the surface like lava lamps in ultra-slow motion? Thermal models suggest that if a plume of warmer ice nears the surface, it might vaporize suddenly, leaving a void for the overlying ice to sag into. The polygon's uniformity might then reflect the natural cell-like patterns of convection, like bubbles in a pan of simmering syrup. Then there's the wild card, chemical erosion. Pluto's nitrogen ice isn't pure, it's laced with methane and carbon monoxide, each compound sublimating at different rates. Imagine pouring acetone onto styrofoam. The solvent eats through the material in uneven patches. On Pluto, sunlight could be triggering similar reactions, with methane acting as a corrosive agent that etches pits faster in some areas than others. Spectral data even hints that the pit's edges are enriched in methane, as if the gas pooled there before vanishing into the sky. The most tantalizing clue lies in the pit's depth. Some plunge hundreds of feet, far deeper than sublimation alone should allow. This raises a radical possibility that they're not surface features at all, but skylights into a hidden underworld. If Sputnik Planish's ice sheet conceals caverns or porous layers, pits might form where the ceiling collapses, like sinkholes in limestone. A few even appear to have debris piles at their bases, as if material crumbled inward from below. Could we be looking at the rooftops of subterranean chambers, where nitrogen rivers once flowed or still linger as slush? What makes these pits more than geological curiosities is their impermanence. Unlike impact craters or mountain ranges, they're ephemeral, likely forming, emerging, and vanishing over thousands of years. Their presence proves that Sputnik Planitia isn't just a static slab of ice, it's a dynamic skin, constantly reforming itself in response to hidden forces. And if we could watch them evolve in real time, we might finally crack the code of Pluto's restless glaciers, watching as these geometric scars breathe in and out, whispering secrets of the ice they're slowly consuming. Pluto's atmospheric haze isn't just a uniform blanket, it's a patchwork quilt of varying density and structure, shifting dramatically from one region to another like weather patterns on a planet-sized scale. When New Horizons peered back at Pluto's limb just after closest approach, it captured something astonishing. The haze layers weren't uniform. Some areas boasted over 20 distinct, wispy bands stacked like pancakes, while others showed only a handful, blurred into a milky glow. Even more puzzling, these variations didn't follow any obvious geographical logic. The haze above Sputnik Planitia, for example, appeared denser and more intricately layered than the thinner veils stretching over Cthulhu Macula's dark plains. What could possibly cause such inconsistency in the sky of a world barely larger than Earth's moon? One clue lies in the interplay between surface composition and sunlight. Pluto's brightest regions, like the heart-shaped Tombaugh Regio, reflect vast amounts of solar energy back into the atmosphere, energizing chemical reactions that spawn haze particles. Nitrogen and methane ice sublimating from Sputnik Planish's glaciers might act as a factory, pumping fresh gas into the air where ultraviolet light can fracture and recombine it into tholins. Meanwhile, darker terrains like Cthulhu Macula absorb heat instead of reflecting it, creating localized dead zones where the atmospheric chemistry simmers rather than boils. Think of it like Earth cities versus deserts. Urban heat islands churn out smog, while arid regions stay clear. Pluto's version is just scaled down, with ice fields playing the role of smokestacks and soot-stained plains acting as atmospheric sponges. But sunlight isn't the only sculptor. Pluto's wobbly rotation and extreme axial tilt create microclimates where atmospheric circulation behaves unpredictably. Winds, though whisper-thin, might funnel haze particles toward certain longitudes, stacking them like sediment in a river delta. Some models suggest that tidal forces from Charon could even distort Pluto's atmosphere, compressing haze layers on one side while stretching them thin on the other. The result? A sky that's not just layered, but textured, thick where forces conspire to trap particles, wispy where they're starved or scattered. The wildest twist comes from seasonal changes. As Pluto inches away from the Sun over the next century, its atmosphere should collapse but not uniformly. Areas with active sublimation, like Sputnik Planitia, might cling to their hazes longer, creating temporary haze oases while the rest of the world darkens. This could explain why New Horizons saw such stark contrasts. It might have caught Pluto mid-transition, with some regions already shutting down their atmospheric engines while others ran at full tilt. What makes these variations more than a curiosity is their defiance of expectation. On Earth or even Mars, atmospheric patterns follow clear rules: pressure systems, topography, solar exposure. Pluto's hazes play by different physics, where weak gravity, exotic chemistry, and microclimates conspire to paint the sky in strokes we're only beginning to decode. And if a world this small can host such complexity overhead, what does that mean for other dwarf planets, where conditions might be even stranger? The answer is written in those wispy layers, waiting for the next mission to read them. Deep beneath Pluto's fractured ice, a tantalizing possibility lurks: a hidden ocean of liquid water, defying the bitter cold of the outer solar system. It sounds like science fiction, but the evidence is mounting that this tiny world might harbor a subsurface sea, kept liquid by forces we're only beginning to understand. The idea hinges on Pluto's surprising geological activity, from its convecting glaciers to its cryovolcanoes, all hinting at an internal heat source that shouldn't exist in a world so small and distant. Could a buried ocean be the engine powering these mysteries? One of the strongest clues lies in Sputnik Planitia, Pluto's heart-shaped basin. This sprawling nitrogen ice sheet sits suspiciously well-balanced, almost perfectly aligned opposite Pluto's largest moon, Charon. Such precise positioning suggests something massive lurks beneath the ice, offsetting the basin's weight like a counterweight in a cosmic scale. An underground ocean, dense with dissolved salts or ammonia, could explain this anomaly. As the water sloshes beneath Pluto's crust, tidal forces from Charon might have shifted it over time, dragging the basin into its current alignment like a ship's ballast stabilizing in choppy seas. Then there's the chemistry. New Horizons detected ammonia compounds near fractures and cryovolcanic regions, a telltale sign of antifreeze at work. Ammonia lowers water's freezing point dramatically, allowing liquid to persist even in the deep cold of the Kuiper belt. If this ammonia-rich water occasionally breaches the surface, perhaps through cracks or volcanic plumes, it could explain the youthful, crater-free patches that baffle scientists. Imagine a frozen lake with springs bubbling up through the ice. Pluto might have its own version, oozing briny sludge that refreezes into smooth plains before impact scars can accumulate. But not everyone's convinced. Critics point out that Pluto's size works against it. Most small icy bodies lose their internal heat billions of years ago, and without enough radioactive elements in its core, Pluto shouldn't have the energy to maintain a liquid layer. Even tidal heating from Charon, while plausible, might be too weak to do more than slightly warm the ice. Some argue that the observed features could instead stem from exotic ices like nitrogen or methane, which behave unpredictably under extreme cold and pressure without requiring liquid water at all. The strongest counterargument comes from Pluto's surface fractures. If an ocean exists, it would freeze and expand over time, cracking the overlying shell into distinct patterns, yet some of Pluto's fractures don't match the expected stress models for a freezing sea. Instead, they might trace back to tectonic shifts or even ancient impacts, leaving the ocean hypothesis in limbo. But here's where the plot thickens. Recent simulations suggest Pluto's ocean wouldn't need to be global to explain the evidence. A regional sea, tucked beneath Sputnik Planitia, could account for the gravitational anomaly while requiring far less heat. Alternatively, the ocean might be more sludge than water, a thick, briny mix with the consistency of toothpaste, sluggishly deforming under pressure rather than flowing freely. Such a compromise could reconcile the conflicting data, offering a middle ground between outright skepticism and full-blown aquatic optimism. What's at stake isn't just Pluto's reputation as a dynamic world. If even this diminutive dwarf planet can cling to a subsurface ocean, the implications for habitability and life in the outer solar system become staggering. Moons like Europa and Enceladus have stolen the spotlight, but Pluto's potential ocean suggests that liquid water might persist in the most unexpected places, wherever antifreeze compounds and residual heat conspire against the cold. Whether the evidence ultimately holds or not, the debate itself reshapes our understanding of how small, icy worlds evolve, and where we might one day find the next clues in the search for life beyond Earth. Among Pluto's most surreal landscapes lies a patchwork of terrain so bizarre it looks like the shed skin of a cosmic serpent, ridges of ice folded into overlapping scales, their edges crisp and reptilian under the dim sunlight. This so-called snakeskin terrain, spotted by New Horizons in the Tartarus-Dorsa region, defies easy explanation. Unlike the bladed methane formations or the smooth plains of Sputnik Planitia, this textured surface appears meticulously crafted, as if some unseen force etched a dragon's hide into the ice. What could create such intricate patterns on a world where temperatures hover near absolute zero? One prevailing theory points to methane's dual personality on Pluto, both as a gas and a frost. When sunlight strikes methane ice, it doesn't just sit there. It sublimates, vanishing directly into vapor and leaving behind a residue of tougher chemicals like tholins. Over countless seasons, this cycle might carve the ice into delicate ridges, with each sublimation event acting like a microscopic chisel. Imagine a block of dry ice left in a freezer, its surface withering into fragile fins as gas escapes. On Pluto, this process unfolds over millennia, with methane frost retreating in waves, leaving behind these scaly undulations, but methane alone might not tell the full story. The snakeskin's precise, quilted appearance suggests something more organized than random sublimation. Some researchers propose that Pluto's weak but persistent winds could redistribute methane grains like sandpaper, sanding the ice into parallel grooves. Alternatively, temperature swings between day and night spanning just tens of degrees but extreme by Plutonian standards might cause the ice to expand and contract, fracturing it into geometric patterns. Earth's deserts form similar, polygonal cracking in mud, though on a vastly smaller scale. On Pluto, the same physics could play out across miles of frozen wilderness, amplified by time and alien chemistry. The most tantalizing clue lies in the snakeskin's location. It clusters near Pluto's rugged highlands, where topography might create microclimates, pockets of slightly warmer or cooler air that alter how ices behave. If methane sublimates faster on sun-facing slopes or lingers in shadowy hollows, these subtle variations could sculpt the terrain into patchy scales, each tile a record of localized climate conditions. Spectral data even hints at methane and nitrogen mixed within the ridges, suggesting a tug-of-war between competing ices, each eroding at its own pace like layers of sediment weathering unevenly. Yet for every explanation, gaps remain. Why do some scales appear sharply defined while others blur into the background? Could seasonal shifts in Pluto's atmosphere, thin as it is, alter the process, leaving some areas preserved like fossils while others reset annually? And why doesn't similar terrain appear on other icy worlds, like Neptune's moon Triton, where methane and nitrogen also dominate? The snakeskin's uniqueness suggests Pluto's recipe: a dash of chemistry, a pinch of climate, and an eon of patience might be unrepeatable elsewhere. For now, this reptilian landscape remains one of Pluto's most poetic mysteries. It's a reminder that even in the stillness of the Kuiper belt, change comes in whispers, etching its signature one molecule at a time. Every scale on this icy hide captures a moment in Pluto's slow dance with sunlight, a dance we're only beginning to decipher. Amid Pluto's dark, rust-stained plains, a series of enigmatic bright spots gleam like scattered diamonds, small yet dazzling anomalies that refuse to fade into the background. These aren't reflections or camera glitches, they're real features, some no larger than a city block, others stretching miles across, dotting the landscape with puzzling radiance. When New Horizons mapped Pluto's surface, these patches stood out starkly against the dwarf planet's muted tones, their brilliance rivaling even the heart-shaped Tombaugh Regio. But unlike Sputnik Planitia's nitrogen plains, which boast a known origin, these bright spots lack an obvious explanation. What's causing these isolated pockets of light in such an otherwise shadowed world? One compelling theory ties them to frost-fresh deposits of nitrogen, methane, or carbon monoxide ice, condensing in Pluto's coldest microclimates. Just as frost clings to shadows on Earth's winter mornings, these ices might accumulate in sheltered hollows or high-altitude zones where temperatures plunge just enough to trap volatiles. Some spots cluster near crater rims or mountain bases, where topography could create cold traps, snatching molecules from the thin atmosphere and freezing them into glittering veneers. The brightest patches might even mark snowfall hotspots, where atmospheric gases crystallize directly onto the surface, like a cosmic version of hoarfrost forming on a window pane. Yet frost alone doesn't account for the spot's irregular distribution. Why do some regions shimmer while neighboring terrains stay dark? Here's where chemistry adds a twist. Spectral data reveals that many bright spots are rich in methane, but not the same kind found elsewhere on Pluto. Some exhibit a purer, almost pristine form of methane ice, unblemished by tholins or other organic contaminants. This suggests these areas might be freshly resurfaced, either by geologic activity or seasonal sublimation cycles. Imagine a cracked glacier exhaling bursts of methane gas, which then refreezes into bright, new ice, a process that could leave behind these radiant splashes like footprints in the snow. But the most electrifying possibility involves cryovolcanism. A few bright patches coincide with fissures or mound-like structures, hinting at eruptions of slushy ice from below. If Pluto's subsurface ocean or pockets of briny sludge ever forced its way to the surface, it could have deposited layers of clean, reflective ice as it froze. The spots might then be the dried-up remnants of ancient icy geysers, their material too young and undisturbed to have darkened under eons of radiation. New Horizons spotted similar features near Right Mons, where possible cryovolcanic flows left bright streaks in their wake. Could these scattered spots be smaller, quieter relatives of those explosive events? Then there's the wild card, radiative cooling. Pluto's surface is a master of thermodynamics, with some materials absorbing sunlight while others deflect it. Bright ices, especially methane, excel at reflecting infrared radiation, which could create localized cooling feedback loops. A patch of methane frost might chill its immediate surroundings just enough to coax more frost from the atmosphere, growing brighter and larger over time, a self-sustaining cycle that amplifies these radiant anomalies. It's a cosmic game of freeze tag, where the brightest spots recruit their neighbors into the glow. The implications stretch beyond Pluto. If these bright spots are indeed dynamic, forming, fading, and reforming over seasons, they'd prove that even the solar system's loneliest outposts are anything but static. They might also serve as beacons for future missions, marking sites where Pluto's internal secrets breach the surface, and if similar features appear on other Kuiper Belt objects like Makemake or Haumea, they could reveal universal processes at work in the frozen fringes of our cosmic neighborhood. For now, these luminous puzzles remain unresolved, each one a flicker of defiance in Pluto's twilight realm. They're reminders that brightness isn't always a sign of warmth. Sometimes it's a clue to the unseen forces sculpting the dark. And in their glow, Pluto whispers a challenge: keep looking closer, because the smallest details often hold the biggest surprises. From its floating mountains to its disappearing atmosphere, Pluto's 25 greatest mysteries paint a portrait of a world that refuses to play by the rules. Every discovery from New Horizons shattered expectations. How could something so small and so cold be so astonishingly alive? Glaciers that flow like wax, skies that glow blue, dunes shaped by winds too faint to feel, and volcanoes that spew ice instead of fire. This isn't the dead, static rock we once imagined lurking at the solar system's edge. It's a dynamic, evolving world with processes we're only beginning to decode, where nitrogen rivers cut valleys and methane snow dusts mountaintops under a sky filled with organic haze. The deeper lesson here isn't just about Pluto, it's about rewriting the story of the outer solar system. If a dwarf planet barely larger than our moon can host such complexity, What does that mean for the hundreds of other icy worlds hiding in the Kuiper belt? Are they too concealing underground oceans, cryovolcanic plumes, or shifting glacial plains? Pluto's defiance forces us to reconsider everything we thought we knew about small, distant worlds. They're not relics frozen in time, they're laboratories of exotic physics, where familiar substances like water, methane, and nitrogen behave in ways that seem ripped from science fiction. But perhaps the most thrilling takeaway is how much we still don't know. New Horizons flyby was a snapshot, a single glimpse of Pluto's long, strange year. What happens when its atmosphere freezes solid in the coming decades? Will Sputnik Planish's polygons keep churning? Could Right Mons wake from its slumber and erupt anew? The only way to find out is to go back with orbiters, landers, even drones designed to skim its hazy skies, so stay curious, follow the data from future missions, because Pluto's greatest mystery might still be hiding. The next chapter in its story could reveal even wilder truths about our solar system's forgotten frontier, and remember, if a tiny world like Pluto can append textbooks, imagine what other surprises are waiting in the dark. The universe never runs out of puzzles, it just waits for us to look closer.